Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.3, which is all about a concept called Gibbs free energy and thermodynamic favorability, which sounds really complex, but is actually a fairly simple concept. So have your equation sheet out and let's get started. So up to this point, we have talked about the concept of enthalpy for a particular process, the change in heat energy. We've talked about the change in entropy. Okay, remember, entropy is a measure of chaos or disorder for a particular process. And both of those concepts, enthalpy and entropy, are used to help us determine if a particular process is favorable, spontaneous. Okay, and the term that the College Board likes us to use is thermodynamically favored. And there is a concept called Gibbs free energy, and it has the variable G for Gibbs free energy. Delta G meaning the change in Gibbs free energy for a particular reaction. And one of the things that delta G is really helpful, really useful for, is determining whether a process is thermodynamically favored or not. Changes in enthalpy and changes in entropy can give us sort of guidance as to whether a process will be favored or not. We can say it'll probably be favored or it's likely that it is. But knowing a value for delta G gives us definitive answers. Yes, it is favored, or no, it isn't. And what this is saying to you on the screen is, if you solve for a value for delta G and that value comes up as negative, that means the process, yes, is thermodynamically favored. It will occur on its own without any outside intervention. This equation right here should look a little bit familiar to you. We have seen an equation very similar to this one, both for delta H, enthalpy, and for delta S, change in entropy. Okay, this is essentially another way you can do products minus reactants. Remember, guys, that little subscript F stands for formation, and the values for the delta G's of formation for both your products and reactants can likely be found in some kind of appendix in the back of your textbook. The textbook I use, it's in Appendix C. Or maybe your teacher has given you a chart with delta G values of formation. You do not ever, of course, have to memorize any of those values. If this were, if we were doing a calculation with this equation on the AP exam, they would have to give you those formation values. So now that we know what delta G is good for, telling us whether something is favored or not, let's just look at an example multiple choice question together. We're given a reaction, we're given the delta H value, and the question says the decomposition of hydrogen peroxide is represented by the equation above. A student monitored the decomposition of 1 liter sample of hydrogen peroxide at a constant temperature of 300 Kelvin and recorded the concentration of hydrogen peroxide as a function of time. The reaction is thermodynamically favorable. Okay, that's important. I'm going to underline that. And then it says the signs of delta G and delta S for the reaction are which of the following? So let's narrow our choices down. We know that the reaction is favorable. Remember what we saw on the previous slide? What does that mean for the value of delta G? It means delta G has to be negative. So A and C I can eliminate. So between B and D, the only difference is the change in sign for the change in entropy. And guess what, guys? This whole chart here is just a distractor. We don't need it at all. To determine the change in S, or to try and predict it anyway, let's look at our balanced equation here. Okay, it's a decomposition. One compound is breaking down into two things. Another thing to look at, remember states of entropy, states of matter. Remember, gases have really high values of entropy, lots of disorder. So this reaction is clearly, from left to right, increasing in entropy. That means delta S is going to be positive. So guys, my answer is going to be answer choice B, because the reaction is favored, delta G is negative, and the reaction is going from one reactant to two products, plus one of my products is a gas. Entropy is definitely increasing. Okay, now just to make sure that you guys remember how to do that whole products minus reactants business, you're given a balanced equation, okay? You are given, look at the chart you're given, and this is the clue here. I see that, whoops, that little subscript F. Okay, I always tell my students, when you see that little subscript F for formation, I want you to think products minus reactants. And that's exactly what you're going to do here. So I want you guys to try this, plug the numbers into that equation, see what you get. All right, let's check your answers. So if you plug in the value of your products minus those values of your reactants, you get 18.22 kilojoules per mole. Just remember, you've got to take those coefficients into account when you're doing any type of products minus reactants situation. Okay, and let's think about what this answer means. The delta G is positive. So what does that mean about this reaction? It is not thermodynamically favored. It is not going to occur spontaneously on its own. In order for this reaction to go and produce products, we're going to have to help it out in some way. Okay. Okay, now we just did an example where we used this equation, but there is another equation for solving for delta G. And guys, I want you to pick up your equation sheets and look at the section on your equation sheet that is labeled thermodynamics / electrochemistry. Okay, it's right here. Oops. Okay, and I want you to notice what is here for you. You have all of these products minus reactants equations. Okay, one for entropy, one for enthalpy, one for delta G, which we've just used. And then you have another delta G equation. And actually there's quite a few, okay, which we're going to get to those later on. But here is this new one right here. And if you look at this one, this delta G equation involves enthalpy, temperature, and the change in entropy. So if you know all of those values for a particular process, the change in enthalpy, the temperature, and the change in entropy, this is just another way that you could mathematically prove if a reaction is favored or not. Okay. All right. So as I said, using this equation that I've just shown you, it's the same one up at the top of the slide here. If you know the value for delta H and you know the value for delta S, and you're also given the temperature, you can calculate delta G and mathematically prove whether a process is favored or not. But what if you don't actually have numbers? You just know the signage, positive or negative, for enthalpy and entropy. You can make a prediction as to whether the reaction will be favored or not. And I say don't memorize this chart. I mean, obviously I can't stop you from memorizing it, but it's a lot easier if you can kind of rationalize through it. Okay. And we're going to take this piece by piece. So I'm actually going to start at the bottom line of this chart. Okay. And this is good review. It's going to sort of pull things together for us. So we're going to start right here. So I want you to think, first of all, what a positive delta H means. Remember, that means an endothermic process. And guys, I want you to really think about what that means. Endothermic. Heat is absorbed. Here's another way to say it. Heat is required for this process. That does not sound to me like a situation that is going to happen on its own. If it's a process where heat is required to make products, that's not a favorable process. And guys, most endothermic processes, most, not all, but most, are not thermodynamically favored. Most endothermic processes are not going to happen on their own without any help. So I'm going to put a little X above that plus sign indicating probably not favored. Okay, now let's think about what a negative delta S means. Negative delta S means this process is becoming more organized. And as we said in a previous lesson, that goes against what is sort of typical in nature. Things in nature tend to get, quote, messier, more chaotic, more disordered. So a process that is becoming more organized is also not likely to be favored. When we have this combination here, where I'm getting two situations where it's not likely to be spontaneous, favored, guys, this is a combination that will never be spontaneous, will never be thermodynamically favored. Now, that doesn't mean that this is a reaction that can't occur. It just means that whatever this process is cannot occur without help. Like maybe we have to add heat to it to get it to go. So positive delta H, negative delta S is a process that will never be thermodynamically favored. Okay, let's come up to this line and let's think about what each thing means. A negative delta H, that means exothermic. Exothermic means we have so much heat, we're giving it away. Heat is released, heat is produced. That's the opposite of endothermic. And not all, but most exothermic processes are thermodynamically favored because heat is not required. Heat is actually going to be given off. What does a positive S mean? Positive delta S. Entropy is increasing. This process, whatever it is becoming more disordered. And that is what typically happens out in nature. So that is also likely to be favored. And I've got two check marks here, two situations where they are likely to be favored. So guess what? That means with this particular combination, this is a reaction that will always be favored. It doesn't matter what the temperature is. Okay, this is a reaction that will happen on its own without any help from us. Okay, now let's come here. positive delta H, endothermic, not likely to be favored. Positive delta S, becoming more disordered, well, that is likely to be favored. So guess what? We have conflicting information here. So I'm going to make up some numbers. Let's say the delta H, which is positive, I'm just going to make up a number, is 2,400 joules per mole, and the delta S, which is also positive, let's say that's 30 joules per mole Kelvin. Okay, I want you to direct your attention up here to this equation. I will explain in a minute why I'm doing this, but just go with me for just a moment. I'm going to set delta G equal to 0. I'll explain why in just a moment. And I'm going to plug in these values. 2,400 is my heat, minus T times 30. If you solve this mathematically, T comes out to be 80 Kelvin. And if you'll notice, guys, what this says right here, it says if we have this situation where the delta H is positive and the delta S is also positive, it says right here, favored at high temperatures. What does that mean, high temperatures? In this case, it would mean any temperature greater than 80 Kelvin. So I set delta G equal to 0. I'll explain why I did that in just a second. And I plugged in these values that I was given, and I solved for T. And any temperature greater than that one that I solved for is going to cause the reaction to be favored. If you don't believe me, pick a number greater than 80. Like let's say the temperature is 100 Kelvin. Well, guys, if you take that number 100 and plug it in right there, delta G is going to come out to be a negative number. Well, what does a negative delta G mean? It means it's favored. Okay? So when you have a plus-plus combination, it will be favored at whatever temperature, above whatever temperature you get when you set delta G equal to 0. Okay, last situation, negative delta H, exothermic, likely to be favored. But negative delta S means becoming more organized, not likely to be favored. So we've got this conflicting information again. So I'm actually going to use the same numbers, just making them both negative. And I'm going to plug them in, set delta G equal to 0. I'll explain, just be patient. Solve for T, and guess what? We get 80 again because I used the same numbers, just negative. This one says it's favored at temperatures, at low temperatures, and in this case that means any temperature less than 80 Kelvin. If you don't believe me, pick a number less than 80. Like, let's use something really easy, like 1 Kelvin. That's less than 80. Plug it in right there. I promise you, you will get a negative value for delta G. Negative delta G means favored. So occasionally, guys, you will have questions, especially in multiple choice, where you're not expected to do much math, and you'll be asked to make a prediction on whether this particular combination of delta H and delta S is going to result in a favored reaction. So let's look at this. This question addresses this issue that we were just looking at. So we've got an equation and we're given the delta H value. and it's negative, it is observed that the reaction producing KCl from its elements goes essentially to completion. I'm going to explain in a minute what that means. Which of the following is a true statement about the thermodynamic favorability of the reaction? Well, let me zero in on this phrase right here. Goes essentially to completion. Ladies and gentlemen, I'm going to translate that for you. Is favored. Okay. And if that is the case, let's think about what is the signage then for delta G. It must be negative. Okay, goes to completion means basically all the reactants react as far as they can and make as much product as they can. It's a favored reaction. So I can get rid of B and D. This reaction is favorable. But then it says, to distinguish between A and C, is it driven by the enthalpy change only, or is that favorability driven by both the enthalpy and the entropy? Okay, well, let's think about that chart we were just looking at. A negative delta H, exothermic, likely to be favored. And we know that it is in fact favored because they told us it was. So I know that the enthalpy change is helping out that favorability, but let's look at the entropy. Let's look at the reaction. What would be the sign of delta S? Is this reaction becoming more disordered or more organized? Looks to me like it's becoming more organized, which means that the delta S is negative. And let's review something we looked at on the previous slide. Is a negative delta S something that is typically favored? Yes or no? The answer is no, it's not. Okay, now again, we know that this reaction is favored because they told us, but is the enthalpy helping us with that favorability? No, it isn't. Okay, so D, oh, whoops, not that one, this one. So entropy is not helping us out. The enthalpy, the delta H, is the only thing here that's driving this favorability. Okay, the entropy is not helping us out. Okay. Now, before you do this problem, okay, let me come back. I'm just going to rewrite that equation we just used a moment ago. And you saw me setting delta G equal to 0. Let me tell you why I did that and when it's appropriate to do that. Let's review. A negative delta H means the reaction is favorable. A positive delta H means the reaction is not favorable. So what does 0 mean? 0 is the boundary where a reaction goes from being favored to not favored, or vice versa. Ladies and gentlemen, delta G equal to 0 means you are at equilibrium. Okay, let me say that again. When delta G is equal to 0, that means you're at a place of equilibrium. One of the places that you will very often be at equilibrium is when a substance is going through a phase change. Like melting, for example, or boiling. Okay, so this is a big clue that if you ever see the fact that you're going through a phase change, okay, and you may look at a problem and say, gosh, I'm missing a variable or two. If you're at the melting point or you're going through a phase change at the boiling point or whatever, you're at equilibrium. Okay, so that's just something to kind of keep in mind here. Before you try this problem on your own, let me just call your attention real quick. Units are really tricky in this unit here. Okay, let me just write this equation one more time. If you are trying to plug multiple things into this equation, they have to be in the same unit of energy. For example, I cannot plug something that has joules into the same equation with something that's in kilojoules. You got to convert one of them into the unit of the other. Okay? Just pointing that out. Okay, so I want you guys to pause this video and see if you can answer these questions. All right, let's check it. Now this first question asks, at the top of the slide, you're given the enthalpy, okay, which is delta H of fusion, and you're given the entropy, the delta S of fusion. And the first question says, will solid ammonia spontaneously melt at 200 K? That's basically asking, is this reaction favored, yes or no? And you have some numbers. So to me, it would make sense to calculate, not just predict, but actually calculate a value for delta G and see, is it positive or is it negative? So I used that new equation and I plugged in my values. Please notice, guys, that I changed 5.65 kilojoules. I changed it into joules so that I would have joules throughout my equation here. And my answer came out to be negative. And let's remember what that means. A negative delta G, yes, this will happen. Ammonia will spontaneously melt at 200 Kelvin. Okay, now part B says, what is the approximate melting point? That means T is my unknown. Okay, I have this, and again, guys, we're at a phase change. We are going through a stage of equilibrium, so I'm going to set delta G here equal to 0. 5650 minus T is my unknown. I'm running out of room here, but T comes out to equal 196 Kelvin. So that is the melting point of ammonia. Okay, now come back to letter A. Look at the temperature in letter A. It's hotter than 196. Okay, so it should make sense to you that if you're above the melting point, solid ammonia should spontaneously melt. It's like having ice at 15 degrees Celsius. Well, ice melts at, freezes it, melts at 0. If you're anywhere above the melting point, it should spontaneously melt, and letter A is showing us that mathematically that yes, that is true. Okay, so what I want you guys to do, this is a free response question, and it kind of pulls a lot of concepts all together. So I want you to pause the video and try these parts A, B, and C of this question and see how you do. Okay, let's check your answers. So we have this equation, and the first thing we're asked to do is to predict the sign of delta S and justify the answer. So I said delta S will be positive because the reaction has 1 mole of gas in the products and no moles of gas in the reactants. Remember, guys, gases are sort of a definitive thing when you're deciding the delta S value because gases have a tremendous amount of entropy. There's a gas on the right-hand side, there's no gas on the left-hand side. So the entropy is definitely increasing, positive delta S. Letter B gives us some heats of formation. Remember what I said to you. When you see a chart giving you formation values, I want you to have like a light go off in your head. Products minus reactants. And that's exactly what you're going to do. The heats of formation of your products minus the reactants, and we get 43 kilojoules per mole. Last part. Based on your answers to A and B, is this reaction more likely to be thermodynamically favored at 25 degrees or 95 degrees? Remember from the previous slide, delta S was positive, delta H was positive. Let's remember that chart, which I said don't memorize. What is the likelihood here? Okay. If you go back and look at that chart, it says that with that kind of a combination, positive delta H, positive delta S, it says favored at high temperatures. So I'm going to guess that this reaction is going to be more favorable at the higher temperature, at 95 degrees. And I've justified it one way on the slide here, but I'm going to give you another way to justify it. So I said the reaction is more favored at 95 degrees at the higher temperature using the equation we just learned today. T delta S is larger and positive. Thus, when T delta S is subtracted from the positive delta H, the delta G value is more likely to be negative. If that mathematical kind of explanation doesn't work for you, you could simply sort of use reasoning. You could say a positive delta S means increasing entropy, which is likely to be favored, whereas a positive delta H, an endothermic, is not likely to be favored. This combination will become more favored at higher temperatures. You could say something like that. One last thing that I would like to show you all. If you will recall, back from Unit 6, we learned something called Hess's Law. And some of you really like these Hess's Law problems where you're given some elementary steps and you had to rearrange them so that when they added together, it equaled the overall reaction that usually you are given, okay? Hess's law problems work the exact same way. We did them back in Unit 6 with delta H values. It works the same way for delta G values. So let's just review that process. Like if this is the overall reaction I am supposed to end up with. Carbon diamond, where is it? Here it is. Is it on the correct side? Yes. Does it have the correct coefficient? Yes. Fine. I'm going to leave this first elementary step alone. I don't have to flip it around or anything. Carbon graphite. It's on the product side. Well, here it is. It's on the wrong side. It has the right coefficient, but it's on the wrong side. So what do? We're going to flip this reaction around so that it is on the correct side. Carbon graphite. And just like what happened with, oops, not delta H, just like we did with delta H values, when you flip a reaction around, it just changes sign. Okay, so I'm going to scribble through this elementary step because we're not going to use it anymore. I don't want to get confused. Okay, so if I take those two elementary steps and I add them together, carbon dioxide cancels out, oxygen cancels out, and I get left with this reaction. And you don't even need a calculator. What is the overall delta G? Negative 3 kilojoules. Ladies and gentlemen, what does a negative delta G mean? Favored, spontaneous. Okay, and I'm not only showing you this to illustrate the point that you can do a Hess's law problem for delta H values, you can do them for delta G values, you can even do them for delta S values. But the point I'm also trying to illustrate, look at the reaction here. Diamonds are turning into graphite. And I'm telling you, that is a reaction that happens on its own. Just think about that for a second. Now, some of you might be like, wait. Diamonds are going to spontaneously morph into graphite. So do we need to worry about our jewelry spontaneously turning into graphite? You know, I go to my jewelry box and all of a sudden my diamond earrings are graphite earrings. Here's the point I'm trying to illustrate. Just because a reaction is favored does not mean it is fast. This reaction is very, very slow. Favorability and kinetics, ladies and gentlemen, the speeds of reactions have no connection to each other. Okay, you cannot tell the speed of a reaction just based on its favorability. So I just wanted to illustrate that point to you. So that was a lot of material, but I hope that you have learned a little something today, and I look forward to seeing you next time.